Have you ever, just stopped and looked up, maybe caught one of those recent eclipses everyone was talking about?
Yeah.
That moment the sky does something unforgettable.
Oh, absolutely.
Eclipses. They're way more than just the sun going dark for a bit or that kind of spooky red moon.
Much more. They're like these grand cosmic performances.
Exactly. And they hold clues, don't they, to how the universe works. So for this deep dive, we're tackling a big one. The Wikipedia article on eclipse. It's pretty comprehensive.
It covers a lot of ground.
Our mission today, well, it's not just to skim it. We want to really dig in, get the science, the history, some surprising bits, too.
And show why these alignments are, well, so much more than just a pretty sight.
Right. They tell us about time, about light itself, our own spot in the cosmos. Okay, let's unpack this.
Sounds good because, most people think eclipse, they think moon blocks sun or earth blocks moon. Simple enough.
Yeah, the basics.
But the actual definition, it's broader. An eclipse is really any time an astronomical object or even a spacecraft gets temporarily hidden.
Hidden?
How? Well, two main ways. Either it passes into the shadow of something else,
Okay.
or something else passes between it and whoever's watching, you, the observer.
Ah, so it's all about alignment, that perfect lineup. There's a word for that, isn't there? A technical term?
There is. It's syzygy.
Syzygy.
Yeah, it's a great word. It means that precise, nearly straight line configuration of three celestial bodies. It really gets at the geometry involved.
Syzygy. Love it. Captures that cosmic choreography. Now, the article also mentioned, it made a distinction, how things get hidden. Completely versus partially.
Right, that's crucial. Occultation versus transit.
Explain those.
Okay, so an occultation is when one object is completely hidden by another one passing in front. Think total solar eclipse. The moon totally wipes out the sun's disk.
Okay.
Poof.
Total blockage.
Exactly. A transit is different. That's when the object passing in front looks smaller than the thing behind it. So it just looks like a little dot moving across the face. It's only partially hidden.
Like Mercury or Venus crossing the sun from our view.
Precisely. Same idea, different scale. Both involve something passing in front, but the visual is totally different.
That makes sense. Okay, so understanding that. It brings us to the shadows themselves. Wikipedia talks about 3 parts to a shadow during an eclipse.
Yes, the shadow zones. And where you are in that shadow dictates what kind of eclipse you see. It's all geometry.
So, zone 1.
That's the umbra. It's the darkest central part. If you're in the umbra, the light source is completely blocked.
So for a solar eclipse, that means total darkness.
That's your total eclipse, yeah. Being in the umbra means you're in this really narrow cone of deep shadow. It's why totality is so rare for any one spot on Earth. That perfect alignment is, well, geographically picky.
Okay, umbra means total. What's next?
Then there's the antumbra. Imagine the umbra cone tapering to a point. Go beyond that point.
Okay.
From there, the blocking object looks smaller than the light source, so you'd see it silhouetted, but with a ring of the light source visible all around it.
Ah, the ring of fire.
That's the one. That's an annular eclipse, seen from the antumbra.
Cool. And the third part?
The penumbra. That's the fuzzier outer part of the shadow. In the penumbra, the light source is only partially blocked.
So that gives you a partial eclipse.
Exactly. You see a bite taken out, but not the whole show.
So umbra, antumbra, penumbra. Got it. But wait, for a lunar eclipse, when the moon goes through Earth's shadow, does it hit the antumbra too?
Good question. No, it doesn't. Earth's antumbra actually stretches way, way out, far beyond where the moon orbits, so the moon only ever passes through Earth's umbra or penumbra.
Right, okay. That makes sense. And the article mentions contacts, like specific moments.
Yeah, think of them as cues in the performance. First contact is the very beginning, when the edge of the eclipsing object just touches the edge of the light source.
The start.
Second contact is when it's fully inside, that marks the start of totality or annularity. Third contact is when it starts to move out the other side.
The beginning of the end.
And fourth or last contact is when it's completely clear again. Done. These let astronomers time everything super precisely.
Like cosmic clockwork. And that detail about the shadow's speed. Wow. Yeah, racing across Earth at about 1 kilometer per second.
That really drives home how fast these things happen, how fleeting totality is. Okay, let's bring this back to Earth, literally. Let's focus on the eclipses we see most often, the ones involving the sun, Earth, and moon.
Right, our home system's main events. Solar and lunar.
Why do they happen? We know it's the alignment, the syzygy.
It is, but there's a twist. It's not just about the moon being new or full. The key thing is the moon's orbit isn't perfectly flat with Earth's orbit around the sun.
It's tilted.
Exactly. The moon's orbital plane is tilted by about 5 degrees relative to Earth's orbital plane, the ecliptic. Imagine Earth's orbit is a flat dinner plate.
Okay.
The moon's orbit is another plate, but tilted slightly. Eclipses can only happen when the moon crosses the rim of Earth's plate, basically.
At the intersection points.
Precisely. Those points are called the nodes. The moon has to be near a node, and at the right phase, new for solar, full for lunar, for an eclipse to occur. Ah, the tilt. That's why we don't get eclipses every single month at the new and full moon. The alignment has to be just right in 3 dimensions.
You got it. And that geometry means eclipses only happen during certain windows.
Windows.
Yeah, we call them eclipse seasons. They're 2 periods each year, roughly 2 months long each, when the sun is close to one of the nodes from Earth's perspective. That's when the alignments are possible.
So that explains why you sometimes get a cluster of eclipses close together.
That's right. It's all about those seasons.
Okay, so let's compare them head to head. Solar versus lunar. What are the big differences for someone watching?
Well, they're quite different experiences. Solar eclipses, as we said, moon passes in front of the sun, casts that shadow on Earth.
Right, the occultation or the transit.
And the amazing thing is, from Earth, the moon looks almost exactly the same size as the sun. It's this incredible cosmic coincidence. Their actual sizes are vastly different, obviously, but their apparent sizes match up.
That perfect fit thing.
Which makes totality possible, but also incredibly fleeting and localized. Solar eclipses are brief. Totality might last maximum about 7.5 minutes.
Wow, that's short.
And the path where you can see totality is narrow, maybe 250 kilometers wide at most. You usually have to travel to be in the right spot at the right time.
A real chase.
It is. And think about this. The Apollo 12 astronauts back in '69, they actually saw the Earth eclipse the sun from space. Talk about a unique viewpoint.
Whoa. Seeing our own planet cause an eclipse.
Yeah.
That's perspective. Okay, so solar is brief, narrow path. What about lunar eclipses?
Lunars are different. That's when the moon flies through Earth's shadow. Always happens during a full moon phase.
Makes sense. Moon's opposite the sun then.
And unlike a solar eclipse, a lunar eclipse is visible from basically the entire half of the Earth that's experiencing night at that time.
Ah, so much easier to catch one.
Way easier. They're much more common to see from any one location. And they last a lot longer, too. The whole event can take several hours, and the totality part, when the moon is fully in the umbra, can last from maybe 30 minutes up to, well, over an hour sometime.
Plenty of time to watch. And that's when we get the blood moon, right? That reddish color.
Exactly. Even during totality, the moon usually doesn't disappear completely. It glows red.
Why red? I mean, it's in shadow. Shouldn't it be dark?
You'd think so, but it's thanks to Earth's atmosphere. Imagine sunlight skimming past the edge of the Earth.
Okay.
Our atmosphere acts like a lens, bending that sunlight. But it also scatters the blue light more effectively. Same reason our sky is blue and sunsets are red.
Ah, the scattering effect.
So it's mostly the longer, redder wavelengths of sunlight that get bent into the Earth's shadow and fall onto the moon. It's like all the sunrises and sunsets of Earth are being projected onto the lunar surface.
Wow. So Earth's atmosphere paints the moon red during an eclipse if we had no atmosphere.
The moon would likely be almost completely black during totality.
Fascinating. So the bottom line for you, the listener, lunar eclipses. Much higher chance of seeing one from your backyard. Total solar eclipse. Start planning that road trip.
That sums up pretty well. One's common, the other's a pilgrimage.
Okay, let's shift gears a bit. Away from the pure science and into, well, the human side of things. Eclipses have had a huge impact on history, culture, our whole understanding of the cosmos.
Oh, absolutely huge. For starters, ancient records of eclipses are like historical anchors. They help us date things incredibly precisely.
Time markers.
Exactly. There's a Syrian clay tablet, for instance, that recorded a solar eclipse way back on March 5th, 1223 BC. Think about that.
Incredible.
And Chinese astronomers kept meticulous records for over 3,000 years. Modern scientists have actually used those ancient eclipse timings to measure tiny changes in how fast the Earth spins over centuries.
No way. They used ancient eclipse data to measure Earth's rotation changing.
Yeah. It tells us about things like tidal friction slowing the Earth down. The insight there is just wow. These ancient skywatchers with no telescopes were recording data that helps us understand planetary physics today.
That's mind-blowing. And it shows people were trying to figure out the science behind them early on, right?
Definitely. You had Greek philosophers like Anaxagoras around 500 BC figuring out the moon shines by reflected sunlight, a key step.
Right.
And then in India, 5th century AD, the mathematician Aryabhata wrote this treatise, the Aryabhatya. He gave really accurate scientific explanations for both solar and lunar eclipses.
I read about his calculations. Didn't they test them much later?
They did. For a lunar eclipse in 1765, Indian computations based on his methods predicted the timing, and they were only off by 41 seconds. The best European charts at the time were off by 68 seconds.
41 seconds. That's stunning accuracy for calculations done over 1,000 years earlier. It just shows the power of observation in math. Makes you wonder what else they understood.
It really does. And that growing scientific grasp, it gradually started to change how people saw eclipses. By the 1600s in Europe, you had astronomers publishing books, diagrams, trying to explain them.
Taking away the mystery, maybe? Or some of the fear?
Exactly. Booksellers even printed these things called broadsides, like informational flyers, sometimes using science, sometimes maybe a bit of astrology, but the goal was often to calm people down, explain what was happening.
But even with the science,
Yeah.
that feeling of awe, it never really leaves, does it? I remember reading about Gene Weingarten, the writer, calls himself a devout atheist.
Oh, yeah.
He wrote about how total solar eclipses still bother him because they seem too perfect. Like, why is the moon exactly the right size and distance to cover the sun so precisely? It hits you on a different level.
That's a great point. It taps into something deep, doesn't it? And for most of human history, that something deep was tied up in myth and religion.
Right. Fear seemed common.
Very. The Roman historian Cassius Dio wrote about Emperor Claudius back in 45 AD. Claudius actually published a prediction for an upcoming solar eclipse. Why? To stop the public from panicking shows you how disruptive they could be.
So what were some common myths?
A lot of cultures saw it as like a cosmic battle, the sun or moon being attacked or swallowed by some dark force, a demon, an animal.
Like the Norse wolves.
Exactly. Like Skull and Hati, the wolves forever chasing the sun and moon, an eclipse was when they caught them. Or in Hindu traditions, eclipses could be seen as signs of angry gods. People would chant hymns, fast, bathe in the Ganges for purification.
Trying to appease the gods or ward off evil.
Pretty much. Even in early Judaism and Christianity, eclipses were often interpreted as signs from God, sometimes displays of power, sometimes, especially the blood moons, as omens, maybe foreshadowing judgment or the fall of enemies.
So whether it was science trying to explain it or mythology trying to give it meaning, these events just grab people's attention across the board.
Absolutely. They forced us to look up, to wonder, and maybe to feel a little small, but also deeply connected to the cosmos. They shaped how culture saw the universe and their place in it.
Okay, let's widen the lens again. If we connect this to the really big picture, eclipses aren't just an Earth-moon thing, are they? They happen everywhere.
Oh, definitely. All over the solar system and beyond, and looking at them elsewhere tells us even more.
Like where?
Well, think about the gas giants. Jupiter, for example. It's got lots of big moons, and its axis isn't tilted much relative to its orbit.
So more alignments.
Way more frequent eclipses. You can often see the shadows of its big moons, Io, Europa, Ganymede, Callisto, drifting across Jupiter's cloud tops. They look like little bullseyes.
Cool. And wasn't it Jupiter's moons that led to a huge discovery? Something about light.
Yes. Ole Römer, back in the 1670s, this is amazing, he was carefully timing the eclipses of Jupiter's moon Io when it disappeared behind Jupiter or reappeared. And he noticed the timings were off depending on where Earth was in its orbit. When Earth was farther from Jupiter, the eclipses seemed to happen later than predicted. About 17 minutes later, when Jupiter was on the far side of the sun.
So he thought Jupiter was slowing down.
Not Römer. He figured it wasn't Jupiter being weird, it was the light taking extra time to travel the extra distance across Earth's orbit to reach us.
Whoa. So he used Jupiter's moon eclipses to estimate the speed of light for the first time.
Basically, yes. He made the first quantitative estimate. It was revolutionary. And later, Giovanni Cassini used those same precise eclipse timings, not for astronomy, but to help remap France more accurately in 1679.
That's incredible. From Jupiter's moons to the speed of light to making better maps of France. What a connection. What about the other big planets? Saturn,
Uranus, Neptune. They have eclipses too, but they're less frequent than Jupiter's. Their moons often have orbits that are more tilted relative to the planet's path around the sun.
Ah, that tilt again. Less chance for Suzuki.
Exactly. Like Saturn's big moon Titan. It only lines up for eclipses, crossing the sun's path roughly every 15 years or so during Saturn's nearly 30-year orbit. Much rarer.
Okay. What about closer to home? Mars.
Mars is interesting. Its moons, Phobos and Deimos, are tiny. Too small to cause a total solar eclipse from the Martian surface. They can only cause partial ones, or transits.
Just little dots crossing the sun.
Pretty much. But eclipses of the moons by Mars are really common. Mars's shadow sweeps over them hundreds of times each Earth year. And sometimes Phobos even eclipses the smaller, more distant Deimos.
Seriously. One Martian moon eclipsing the other.
Yep. And our rovers, like Curiosity and Perseverance, have actually taken photos of these Martian solar eclipses and moon eclipses. We're getting pictures of eclipses on another planet.
That's just wild. What do we learn from those?
They help us pin down the moon's orbits with extreme precision, learn about their shapes, even probe the thin Martian atmosphere when the sun is low. Every little bit helps build the picture.
And even Pluto.
What?
Way out there.
Even Pluto. Pluto and its largest moon, Charon, are quite big relative to each other. Between 1985 and 1990, they were perfectly aligned, so they eclipsed each other constantly as they orbited.
Mutual eclipses.
Yeah, every few days. By carefully measuring how the total brightness dipped when one passed in front of the other, astronomers got the first really accurate measurements of their sizes and even rough maps of their surfaces, all from watching shadows.
Amazing. What about the inner planets, Mercury and Venus? No moons there.
Right, no moons means no eclipses on those planets.
Yeah.
But from Earth, we can see them transit across the face of the sun.
We mentioned those earlier.
Yep. Venus transits are super rare. They happen in pairs 8 years apart, but then more than a century till the next pair. Mercury transits are more common, maybe 13 times a century. Historically, timing those transits was a key way to figure out the distance from Earth to the sun.
So it's not just planets and moons. Stars do this too.
Oh, absolutely. We call them eclipsing binary systems. Two stars orbiting each other, and if their orbit is edge-on from our perspective, one periodically passes in front of the other.
Blocking the light.
Exactly. The classic example is Algol, the demon star. Its brightness dips noticeably every 2.867 days. John Goodricke figured out back in 1783 that it wasn't one star acting weirdly, but a dimmer star regularly passing in front of a brighter companion.
So observing these stellar eclipses tells us about the stars themselves.
Immensely. By watching how the light changes, we can figure out the star sizes, their masses, sometimes even their shapes and surface temperatures. It's one of the most powerful tools we have for studying stars far beyond our solar system.
Wow. What a trip this has been. We started with, the basics of shadows here on Earth, and we've gone all the way out to stars eclipsing each other light years away.
We really covered the spectrum, the definition, how they work here, their impact on us humans, and then seeing them play out across the cosmos.
It's amazing how much we've learned.
And it really makes you wonder, doesn't it? How can these simple-seeming alignments, just things lining up, give us such deep insights? From ancient calendars to the speed of light to the details of distant stars.
Yeah, it's incredible, the power of just looking up carefully.
Persistent observation and thinking it through.
It really is that mix, isn't it? The cold, hard science and geometry, but also that feeling of sheer wonder, that perfect fit thing that just grabs you. So maybe for you, the listener, here's something to chew on. Every single eclipse, whether it's our moon blocking the sun or Jupiter's moon casting a shadow or two distant stars doing their dance, it's a moment of perfect alignment, a cosmic clock ticking. What does that precision playing out all across the universe tell us about how everything is connected? And what does it say about us being here, being able to witness and even understand these spectacular fleeting shows?